Here we go again. Walk like I mean it. Yeah. Talk.
All right,
like
today we're
I
going to
mean
talk
it.
about the concept of maximum power transfer. This is summed up in what is called the Maximum Power Transfer Theorem. And the basic idea is that there is a way to control the rate at which energy is transferred to a load. So let's say that we've got a fancy network, a resistive network here, which we'll draw as a black box. And that's it right there. Now you know that this fancy network, regardless of how complicated it is, can be simulated by a Thevenin equivalent that looks like that. So if we connected this up to a load, now what could this load be? Well, if this is maybe a transmitter, then this could be an antenna. Whatever it is, maybe this is an engine that needs a large amount of energy quickly delivered. So this is R sub L, the load, and we'll connect it up with wires like that. Well, because we are simulating the resistive network with a Thevenin equivalent, what happens at the terminals is going to be exactly the same for both of these. So we can simulate the load here just as easily. Now if we connect up this is a really simple circuit. And you can see, we can think of that as a voltage divider. Any current that's going to travel through the load, then you can easily calculate the current this way. Current is just going to be voltage divided by resistance. The voltage involved is VTH, and the resistance involved is RTH plus R sub L. Okay, that's the current. Now if you want to compute the power that's transferred, then power is equal to I squared R, and the R in this case is R sub L. So this is the amount of power that's being transferred to the load. If we substitute in for I, then we get that. You may say, if we want to maximize the power transfer, if we want to get more power over here to the load, then we could maximize I, just increase the current. But look here, the current itself really depends upon the load. So if we have some control over the load, and typically that might be true, you'll have more control over the resistance of the load than you do over the network that you're connecting to, then it may be possible to adjust the load value, because by adjusting the load value, you're going to adjust the current and this term out here as well. Well, first of all, think about the general shape of what this power curve is going to look like. If you were to graph this function, power on this axis and R sub L on this axis, then what you would see if you were to graph this for fixed values of RTH and VTH, you would see that the power increases to a maximum value, but then it goes down to nothing in the limit. It approaches zero in the limit. So there is a maximum value right here. The question is, what does R sub L have to be in order to get that maximum value? And while we're here, what is that maximum value? What is the maximum power that can exist for any specific circuit? So how do you find the maximum? Well, this is a first semester calculus type of problem. What you want to do is take the power function, which is this right here, and you want to maximize it. R sub L is the variable. So how do you do that? You take a derivative, dp dr sub L. So that's the derivative with respect to R sub L of the function right here. And let's rewrite that. All right, so we've rewritten the function, which was the I squared R sub L, this way, and that's a -2 right there. And I do that just because I can remember the product rule over the quotient rule every day. And when we take the derivative, the VTH is going to be a constant, so we could even factor that out, VTH squared. And now let's do the derivative of these two terms. We need the product rule. It's going to be the first times the derivative of the second, so RTH plus R sub L to the negative 2, that's the first, times the derivative of the second, which is just going to be 1, plus the second times the derivative of the first, which is going to be that right there. Okay, well, we can kind of reduce the terms a little bit, simplify it, and write it once again as a fraction. All right, let's find a common denominator now. Simplify the top. And that's the derivative right there. We want to set that equal to 0. When is that derivative equal to 0? Well, it would be equal to 0 if VTH is equal to 0, but to be honest, VTH will never be 0, because if it is, why are we even here? That means there is no energy being transferred to the load because VTH is 0. So what does that mean? That means that this top portion of the fraction must be equal to 0. And when does that occur? That occurs when RTH and R sub L are equal to each other. So at RTH is equal to R sub L, then the derivative is equal to 0, and we are at that maximum point. So going back to our graph right here, what does that mean? That means that when R sub L is equal to RTH, then the maximum power occurs. And then what is that maximum power? Well, once again, the power equation was I squared R sub L. Substitute in RTH for R sub L, and you end up with that's the maximum power. So the maximum power theorem says this: you will get a maximum transfer of power when your load is equal to your Thevenin equivalent resistance. That means that if you have the ability to adjust the load resistance, you can adjust it so that it matches the Thevenin resistance, and then you're going to have the maximum power transferred. And the maximum power that can be transferred is going to be this right here for your specific circuit. All right, let's use this information then to work a problem. All right, so here is the circuit that we've got, and we want to transfer the maximum amount of power possible to the load resistance here. Well, to do this, we need to first determine the Thevenin equivalent for the circuit that's on the left. That means we need to be able to replace all of this with one source and one resistor. Like that. Now, if we want to determine what R sub L should be, we only need RTH, because maximum power is going to be transferred when R sub L is equal to RTH. However, if we want to know what the value of the maximum power is, then in that case we need VTH in order to compute that. So let's find RTH and VTH. Let's start with RTH. We're going to disable the 9-volt source here. And let's put a test source over here so that we can then compute what RTH is. All right, there is our circuit with the 9-volt disabled. And we don't have the load hooked up because this is what we want to find RTH from. So let's put on our test source. And that's going to be, we'll make it 1 volt. And we need this current, I naught. Once we find I naught, then RTH is just going to be V naught over I naught. Okay, there are a number of ways to do this. Let's use node voltage method for that node right there. We'll call that voltage V1. And this will be our reference node at the bottom. Then we can write a node voltage equation. V1 over 60 plus V1 minus 3 v sub x over 30 plus v1 minus v naught over 120. And that's equal to 0. All right, you can see that this last term right here is the current that's going to the right, so that's going to be negative I naught. So this term right here is negative I naught. You'll also notice that V1 here is the voltage across the 60 ohm in reverse. So we can write a couple of other constraint equations that V1 is equal to minus V sub x, and I naught is equal to minus V1 minus V naught over 120, like that. Okay, if we make these substitutions here into our node voltage equation, then we end up with this. And I went ahead and substituted in V naught as 1 volt, and that's where that 1 came from there. Okay, let's find our common denominator and group our similar terms now. The common denominator is going to be 120. All right, so we've got 12, 34, 50, 60, 70, 18, 19, negative 19 v sub x is equal to 1. So there's our value for v sub x. That means v naught is going to be 0.053 volts. And now that we've got v naught, we can go back to this equation right here, and we can compute, I'm sorry, I wrote v naught, that should be v1, not v naught. But nevertheless, we go back to this equation right here and plug in this value for v1 and 1 for v naught, and we should be able to compute our I, which is what we're after, so that we can get our RTH. Let's do that. So 7.892 milliamps. Now, there is a sign attached to that here. However, when we go to compute RTH, we know that RTH is always going to be positive, so you may ignore that sign. You can't ignore the sign while you're computing, but once you've got it, then you can ignore the sign to compute RTH. So RTH is V naught over I naught. You can think of that as absolute value. So that's 1 over 7.892 times 10 to the negative 3. And that turns out to be 126.7 ohms. Therefore, if we want to have the maximum power transfer, then we let our load equal 126.7 ohms. All right, now let's find VTH so that we can compute what the maximum power will be when we let the load equal this. All right, well, we go back to the original circuit here and use the open circuit condition. What we really want to know is what is the voltage across the two terminals without the load. So this is the circuit we want. All right, so here's what we've got. We want to know what the voltage is across the terminals here so that we can compute the max power. And you'll notice with the open circuit condition here, there is no current passing through the 120. If there's no current passing through the 120, then there'll be no voltage drop there, and we may ignore the 120 for the purposes of computing VTH. So really, VTH is going to be the voltage from that point to that point right there. Ignore the 120. Now, if we do that and we say that this is VTH and we treat this down here as our reference node, we can write a node voltage equation for that one node. So there's our node voltage equation for that one node. And what we can do is, you may also notice that I left off my V sub x here. So with that in there, you notice that VTH plus V sub x is 9 volts. So if I started down here at the reference node and I went a rise of 9 volts and then a drop of V sub x, then I end up at VTH. That's what this statement right here is saying. But this statement right here, I'll substitute this into the top equation, and when I do that, we get this. We get that right there, which we can solve that for VTH now. Let's find a common denominator and group our like terms just like we always do. Looks like the common denominator is going to be 60. So VTH is 63 over 9, which is 7 volts. So there's our VTH value. Now that we've got VTH, we can compute the maximum power. So P max is equal to VTH squared over 4 RTH. .97 milliwatts. So 97 milliwatts is the maximum power that we can possibly transfer to the load if the load resistance is equal to the Thevenin resistance. And that is the maximum power transfer theorem. We've worked a problem, you've seen how to do it. It's not much more complicated than that, but it is a pretty powerful idea that any circuit can be reduced down to a Thevenin equivalent, and then you can figure out what the maximum power can be transferred to a load is. And this is it. I hope you enjoyed it as much as I did. See you next time.
Here we go again. Flex, walk like I mean it, yeah. Talk like I seen it, yeah. Live it, cause I dreamed it. You could've did it too, but you didn't mean it. Light up like a phoenix. Ooh, I'm hot, yeah, beaming. I'm really here to get the people what they needed. Somebody built Fort Tough, hard cold like a Nene. I'm bad, how bad? Yeah, I'm good, so good. Yeah, I'm strong, so strong. Something you wish you was. I'm back now, I'm back. Don't back down, I'll never back down. I'm back now, I'm back. Look at my crown, I never back down. I'm back now, I'm back. Always stand up, always stand proud. I'm back now, I'm back. Always stand up, I'll never back down. Yeah. Level up. Level up. You can beat me, man, you dreaming. You ain't even if your name is Steven. You can stay there, cause I'm leaving. In a spaceship coupe with the windows tint. Looking down through the clouds saying, man, I'm lit. You can get here, but you gotta work for it. Even when you lose, dog, you gotta kill that shit. Until the whole damn world feel that shit. Yeah, I'm bad, how bad? Yeah, I'm good, how good? Yeah, I'm strong, so strong. Something you wish you was. I'm back now, I'm back. Don't back down, I'll never back down. I'm back now, I'm back. Look at my crown, I never back down. I'm back now, I'm back. Always stand up, always stand proud. I'm back now, I'm back. Always stand up, I'll never back down. Yeah, nothing's impossible, I make it possible. I'm not gonna lose any day. I'm somewhere tropical, thinking about obstacles that I can get through like every day. Who gonna lose?